My name is Igor, and today I'm going to talk about using self-supervised learning and active learning for data curation. I have myself a background in machine learning and computer vision. I'm currently here in Zurich, and I used to do research at ETH Zurich in the computer vision lab before going to industry. And you all probably have heard about this move now towards more data-centric AI. And that's also like the field where we're active at. Now, a bit background also to myself. I basically did a transition from academia to industry, and I faced many problems. I was working on different projects, most notably ones, image segmentation projects where we had to, for example, do automated segmentation of the sky in videos. You see some examples here on the right side of the slide. It's a very difficult task because you also need very high quality ground truth data. And that's a big challenge, not only for me, but for others in the industry, because annotating data with very high precision takes a lot of time, needs expert knowledge, and it's also very expensive. And when I was doing that, I didn't know in the beginning how much data I have to annotate. And as you all know, with deep learning, we have very data hungry systems. So basically we have to label lots of data. And that's a big problem. And what we realized actually when talking to other experts in the field is that there's a bit discrepancy of what is actually good data. It's unclear to most people. Is it about having good labels? Is it about having diverse images which are labeled to train our systems? And what's also very unclear is how much data do we actually need and how much do we need to label? So most companies we work with usually label less than 1% of their data. A bit about the company itself. So I told you a bit about the problems I faced, and we started the company to tackle these problems. We're now venture-backed. We recently joined the Y Combinator program in the US. So we have a base here in Europe, but also in the US. Now, I'm going to mostly talk about unstructured data. So I'm referring to images, videos, audio, or text maybe, but not so much about tabular data because we don't have the same requirements for labeling as with images, for example. Here on this slide, you see a very simple setup. On the left side, you see that we have images, images of cats because we all love cats. And on top of the images, we have the labels. And both together are combined, and I refer to them as ground truth. So this is what we need to basically train a system. You can train a classifier or object detection model or an image segmentation model. Now, when we have this ground truth data, we can also use the labels and the images to query what or understand what kind of data we actually have. So for example, in this context here, we could look for images with at least 2 cats or images that have large cats. So basically the labels here help us to better understand the unstructured data. And that's very important because in large teams, it's a big problem to understand what kind of data do we actually have and what is missing. Now, the challenge is that with this setup, we of course need to label the data. And before we label the data, we don't really know what's in there. So it's a bit a chicken egg problem. And the big thing we try to do here is we try to approach a problem by understanding the data before labeling. So we're kind of trying to just take the raw information like images and try to understand what's actually in there and which subset should be labeled in the end. And we use 2 approaches to tackle this problem. One is called active learning, and the other one is self-supervised learning. If you look at the image on the left side, you see a typical pipeline in a machine learning company. We usually collect data, and then the first thing we do is we select a subset. If you have very little data available, you probably select all of it. And then you label the data, and then the next step, you train the model. Now, it might happen that there's more data available that is unlabeled, and you want to pick a next subset for labeling and improving the model. So we kind of want to create a feedback loop. And we can do this using active learning. So what we do basically is we take the model predictions into account, and we try to fetch a next good batch of example images that should be labeled and then used to train our model in order to improve as much as possible. So the goal is kind of to improve the model in the most efficient way by only labeling what's really necessary. Now on the right side, we have the famous cake analogy. Maybe you heard of it, from Jan LeCun, which is one of the Turing Award winners. Basically, the image should illustrate a bit how much of a feedback signal you get when you train a system. When you look at the cake here, you see that on the top of the cake there is a cherry, which is some very small, juicy, tasty thing. And this is typically what happens in reinforcement learning. And we have a very, very small feedback signal. So if you have ever trained an agent or a robot doing something, and the system has to do many actions, take many steps until there is a reward. And so the feedback signal is very, very slow. And the icing of the cake here in this image, it's referred to supervised learning, because the feedback signal is already more than just a cherry on top. And this is the example here, maybe image classification or object detection or segmentation. Some of the tasks have a lot of feedback. For example, segmentation models get a class for each of the pixels in an image. So they learn a lot about the semantics, the size of objects and everything. So there's a very strong feedback signal. And now with self-supervised learning, in the analogy here, we refer to the whole core, the center of the cake. It's a lot of content there because we have a very strong feedback signal. We have, for a few images, we can learn or extract a lot of information. And how this really works, we will have a look at now in this slide. So I talked about this self-supervised learning, which might appear a bit magical. It's basically the same as what we used to refer to as unsupervised learning. So we don't have labels, we don't have human supervision during the training process. And there are prominent examples here, maybe you heard about, I guess in natural language processing, or the task when you work with text. Very famous is BERT, the model from Google. I think they introduced it in 2017. And then in computer vision, there are other papers. In 2020, there was one which was pretty important as well, which was SimClear. And how do these systems work? We have here in the image on the very right side, the example image from BERT. So we have a sentence with words, and we train a system by masking or removing some of the words of the sentence. And the goal is for the model to predict the missing words. The idea there is very simple, that in order to solve the task of solving this riddle and finding the missing words, the model has to understand the context of the sentence. And the same approach has been also used in computer vision in 2016 already, in a paper called Context Encoders by the lab of Alexei Efros in Berkeley, where we just take an image and we remove part of the image and we train a model to in-paint. So kind of find the missing pixels in the white area in the center in order to reconstruct the original image. And the idea there was very similar. By finding the missing pixels, the model has to understand the context. So the model has to understand there are football players, there are humans, they have 2 arms, 2 legs usually. And the idea there is to train these systems. During this training process, the model learns from the data directly without any labels. And the representations, kind of the knowledge the model gains, can be used then for other tasks. I also have here an example of this SimClear paper to be a bit more specific. You can basically think about these self-supervised learning tasks as kind of trying to create puzzle or riddles for a model. Here you see on the bottom left an image of a dog. This is our input image. And now we can create 2 augmentations of it. These are the 2 images just above. And augmentations can be changes in the image color. We can, for example, turn the image into grayscale, or we can do some random cropping or some other image manipulations. And now out of this one image of a dog, we have 2 augmentations. And we can do this process for all the images in the batch. And then in the end, the model is trained in a way that similar images have to be close to each other and different images have to be far apart. So the model has to learn which two images actually belong together to the original input image. So it's kind of solving the puzzle game in this example here of the head of the dog belongs to the legs of the dog and not to the images from the chair, for example. And by solving this task, the model understands the semantics or the context of the image it has seen. And this works very well, actually. You would be surprised. And it can be used for various things afterwards. Because if you can train a model using self-supervised learning, we can use this knowledge to understand our data. This is also, by the way, what we do at Lightly. So we have here a screenshot on the right side from our platform where we use these embeddings we can extract using models trained on self-supervised learning to visualize the data in a lower dimensional space. So we can basically just cluster similar images that would be close to each other. And dissimilar images would be far apart. And that can be very insightful because very quickly we understand, do we have clusters in our unlabeled data set? Do we have lots of similar images? Or do we have lots of different groups or something? And we can then quickly go or skim through the data and understand a bit more of what might be missing. So what should we collect in the next data collection campaign? Or also whether something might be off. Maybe we collected way too many images in the night and not enough during daytime, for example. The other good side effect of training models using self-supervised learning that has been more and more interesting in the last couple of months is that these models also are very good to be used for a downstream task. So we kind of pre-train models using self-supervised learning and then fine-tune them on a labeled data set. What you see here in this table is a comparison of different models. There's a supervised baseline where we train the model on ImageNet, and then we fine-tune the model on the MS Coco dataset. And this is very commonly done. So we pre-train on ImageNet on the 1 million images as an image classification task, and then we fine-tune the model for object detection or instant segmentation. Now, in the same table, you see the very bottom example, which is the MAE model, the mask autoencoder. And this has also been pre-trained on ImageNet, but this time not with labels, but with self-supervised learning. And as you see in the different accuracy metrics, like the mean average position, for example, for bounding box detection, the metrics are much better. So the model trained without labels achieves a better performance. And once we do the fine-tuning on the Coco data set where we use labels. And this is pretty exciting because this opens a lot of new doors because we have so much unlabeled data set available. Now, it might now be interesting for some of you to try out working with these self-supervised learning models. That's luckily very easily possible. We have our own open source framework. You can find it on the link on the bottom right. It's on GitHub. It's under MIT license, so you can also use it for commercial use. And it has been built on top of PyTorch. It has been built with a lot of modularity in mind and to be also simple to use. And it's currently used by industry experts in tech companies, but also in academia, by research labs. And we're very proud, actually, that we were able to also accelerate research in that field. I will share the link also later for anyone interested in that. So I talked a bit about this self-supervised learning field. Now, I would also quickly summarize a bit the findings about active learning. So as I mentioned before, the task of, or the goal of active learning is basically to select a batch of images that follow certain properties. And there are two main ways to do that. One is based on the features or the embeddings we can extract from the data. And the one common way to do that with images is to use a pre-trained model. And once we have these features, I illustrated them on the right side with an image, you can again see whether there are some clusters or not. And to pick now a subset, maybe just 10 or 20 example images, you can use different methods, such as clustering methods, for example, like k-means, or we can also use methods such as core set selection, where we basically select images that are as diverse as possible. Besides using features, we also can use predictions. It's rather simple. Whenever we run a trained model on a task, for example, for bounding box detection, so kind of object detection tasks, we not only get the location of the bounding box, but we also get the confidence of the model. So the model tells us for one image, I'm 99% sure this is a person. And for another image, it might tell us I'm 50% sure this is a person. And then based on this confidence of the model, we can also make certain guesses on which images might be more difficult, where the model has issues doing the classification, and maybe we should include them into the next batch of images we are going to label. And finally, we can also combine these two approaches. So we can use predictions and the features. This is also something we do at Lightly, which turns out to be very good because we prevent some of the common failure cases. If you, for example, only use predictions of the model, you sort of capture the current state of the model and where it has uncertainties. So if you have an autonomous driving case, and for example, there are cyclists with red code that cause uncertainties in the model, if you would just select all the images with low uncertainty, you might select the same cyclist across different scenes with the same camera angle. And maybe that's not what you want. You don't want to label 100 times or 100 times very similar images. So you still want to have certain diversity, because otherwise you just introduce some sort of overfitting during the training process afterwards. So it's very useful to combine it and use the selection mechanism to select images where the model is struggling, but at the same time images where the images itself are different between each other. Now, I mentioned it briefly before, like how we use that at Lightly, and this is an example here from an autonomous driving data set. It's the Berkeley Deep Drive 100K data set. It consists of, I think, 100,000 videos, which is fully labeled. And in this example here, on the left side, you see the data set, but not the full scenes, but only the crops of the objects. So what we're doing here is we do an analysis of the data set on the object level, and we can look at the distribution now. We can look at, on the right side, you see the embeddings. So we take each of these crops on the left side and we turn them into a vector so we can visualize them in this two-dimensional space. And you see that similar objects are grouped close to each other. So you see the major groups are person, bicycle, bus, cars, and so on. And we can now look at the diversity, for example, of pedestrians in our data set. So we can look whether there are certain clusters of very similar looking pedestrians, or whether there are some outliers of pedestrians which are not very frequent. And this can be very helpful because we basically want to make sure that we cover all possible cases for autonomous driving. We want to make sure that our model learns all the edge cases. And we also want to make sure that we don't label too often the exact same scenarios. So this can be very helpful. This is already now at the end of the presentation. I hope you were able to learn a little bit, and otherwise you can, of course, always reach out if you have some questions. Maybe to conclude a bit, the research field in machine learning is still very exciting. That's pretty important. There's still a lot of progress being made. And now there's a lot of trend towards self-supervised or semi-supervised learning. And the other point is that there's also still a transitioning happening from academia to industry. And then the last point is that kind of state-of-the-art models today in computer vision or NLP are all based on these self-supervised models. So it's pretty exciting to see this progress being made and continuing. Thank you very much.